So, um, so I'm going to talk about fine-grained one-way function, which is a joint walk with Geoffroy. And Geoffroy is sitting in the front row, and there are a lot of parameters. And if I miss some, Geoffroy is going to help me. Okay. So let's start. With NP, one-way functions, average case hardness, public key cryptography, the relations. We're all familiar with that, but it's always nice to take an opportunity to take Russell's stories. So the five swirled story starts with Carl Friedrich Gauss, who was a student once upon a time, and the story is essentially about the dual use of cryptography. So the use in this case is to torture students, as we'll see in a second. And so Gauss had a very nasty teacher who felt tremendously threatened by Gauss as a student, and so he asked Gauss to add all numbers from 1 to 100, and Gauss said, yeah, easy, it's 5050. So that's the moment where you can explain NP to anyone who has never heard about NP, because if you don't know how to make this computation, how do you even check? Right, so how do you know whether Gauss is not cheating? So it's much better if you have a verifiable problem such as a Sudoku. You give it to Gauss. Gauss takes some time to solve it, gives it back, and then you can check that each number appears once per column, per line, and per box, and it's correct. So NP is problems whose solutions are easy to verify. But of course we want hard problems, and so the hope is, or if P is equal to NP, then there exists problems which are hard and which solutions are easy to verify. So now we're going to live entirely in NP, and the way I think about the differences between worst case hardness, average case hardness, one-way functions, and public key cryptography is in terms of quantifiers only. That's the only thing that changes for me. So NP not equal to P means there exist hard problems. The average case version of it is an efficient distribution over hard problems. So you could sample a couple of numbers, put them into the Sudoku, and give them to someone. That would be a distribution of problems that, I don't know, if your number distribution is good, is hopefully hard. One-way functions is, again, a distribution over problems, but together with their solution. So say you sample a random filled-in Sudoku. This is your input to your function. And then you take out a couple of numbers, and that's the image of your function. And then, because you have the solution of the Sudoku, you can solve it later. So we have worst case problems. So of course the important part about one-way functions is that then this teacher who had very hard time to bear Gauss' brilliance could then give this output of the one-way function to Gauss, and if Gauss fails to solve it, he can say, oh well, but I have a solution. Look how great I am. And the paper by Russell continues that if you have public key cryptography, you can come up with problems that everyone in the room can solve, except for Gauss. So you might have an effective means of bearing to have a brilliant student in the class, if that's uncomfortable.
For the arithmetic progression, you can have a short proof, or you can just prove that the sum of arithmetic progression can be computed by short formula, and then you can give the formula. The right teacher cannot verify. That's issue.
Okay. Okay, so the hardness within NP that I'd like to think about is worst case hardness, which means hard problems exist, distributions over problems, which means I have a distribution over problems that are hard, one-way functions, which are distributions over problems together with their solution, and then public key encryption or key agreement, where I have a distribution over problems and solutions, and I can give a backdoor to someone else so they can also solve the problem. And so if we have such distributions, then we can drop the backdoor. Then we have one-way functions, or these distributions over problems and solutions. If we drop the solutions, then we have distributions over problems. And if we have distributions over hard problems, then hard problems must exist. So implications in this direction hold, and in the other direction, we know strong separations. That is in a polynomial hardness world. And so usually when I talk about one-way functions, I say, oh yeah, one-way functions are so important to me because almost everything, oh, well, you need to be careful, but almost everything in crypto implies one-way functions. And if one-way functions don't exist, then I need a new job. Yeah, and most of my work will not be relevant anymore. But this story is not true anymore. Well, has maybe never been true. I could just switch to information theoretic crypto, for instance. But also, it's actually not so bad if everything is a polynomial time algorithm, because there might still be gaps. N to the 100 is a very large polynomial, so if I can compute cryptography very efficiently, but compute a one-way function in linear time, say, and then not invert it with less than n to the 100 time, this would still be very reasonable cryptography. So then the question is whether we can build fine-grained cryptography from assumptions that we understand well. So proving one-way functions in the polynomial hardness world is very hard, because if we wanted to do this, we would need to solve the p versus np problem in the first place. So the only thing that we usually could hope as a cryptographer is to prove one-way functions based on np hardness, but even this we seem not to be able to do. So the question is, if we go to this fine-grained setting, whether we can prove things of this type of flavor. And so maybe we not only go for proving fine-grained results where we have polynomial gaps between computation and inversion, but maybe we are willing to make a little bit stronger assumptions in the worst case. So, for example, assume the exponential time hypothesis, so we know that that then we can build fine-grained hard average case problems. And interestingly, we also know that from exponentially hard one-way function, we can build fine-grained hard key agreement. And so what is missing is the link between these two. So the question, so preferably, it would be nice to prove from the exponential time hypothesis that fine-grained hard one-way functions exist, and what we essentially show in this paper, or it's work in progress, it's not published yet, is an oracle result relative to which there is an exponentially hard language in NP, and there is no fine-grained one-way function. So there are a couple of gaps. So we make our assumption a little bit stronger. We start from a exponentially hard language that is average case hard, has self-amplifying hardness, and instead of starting from NP, we also start from NP intersected co-NP. So NP intersected co-NP tends to be something that tends to be useful for cryptography. So one way of looking at the separation might be that that at least in combination with these attributes, just going a little bit lower within NP does not help. The question that we naturally ask when we see an oracle separation is, how do we get around it? I mean, one way is to think about to understand. Okay, this problem might actually be very hard, but the constructive way of using oracle results, oracle separations, or other type of separations would be to see where we should look. Yeah.
So you have an oracle relative to which there is this language with all these properties.
Yeah.
But it should be easier to prove without these properties.
Yes, it's easier to prove. Like it's easier to prove it. Why we bother? Because it just.
You can?
Because we can.
Okay.
No, I mean, okay. So I mean, there are several results. So the co-NP is because we can. That was that we just observed. We looked at our oracle and said, oh, actually, well, it's an NP intersected co-NP. That's great. The other properties, because they're natural. So self-amplifying hardness would be something where you would think that might help. And
What is self-amplifying hardness?
I'll define it in a second.
But it's very natural.
Huh?
But it's very natural.
Okay, well, okay, then maybe it's not natural. Okay, so it's okay. So essentially, your success probability doesn't get better when you solve several instances. So you essentially have a product success probability. Yeah.
I'm not sure what it means. Like in this domain, if I think about the positive result, say I want to start with the exponential hardness of SAT.
Right.
So it's very clear that my transformation will use SAT, right? And free SAT. So like I would expect to, like when you talk about black box separation, I would expect to see that maybe you cannot reduce fine-grained complexity to SAT via black box to exponential hardness of SAT via black box okay, like the AGGN separation. But here, if the language itself is not like you treat also the language. I mean, so I'm not sure what this thing.
So is it so is it confusing that there are more properties because it's say an NP intersected co-NP and then it's not like SAT would not kind of fall into this class? It's I view it as an even stronger result, but I mean oracle separations are.
My question is the following, so maybe I don't understand the statement. So does it rule out a black box reduction in which that reduces the security of this fine-grained one-way function to solving a SAT in, say, a sub-exponential time or something like this? Like this is the kind of result that I would expect to.
No, it doesn't. But one natural intermediate step, if we wanted to start from exponential time hypothesis to build that, would be to use this paper by Marshall, Alon, and people that shows that from this exponential time hypothesis, you already get average case hard language which are self-amplifying, or non-amortizable, so they amplify well through parallel repetitions and everything. And to start from that and say, well, now I have already this very strong average case hardness, amplifies well, can I go further away and get to an Oneway function? And what it says is that, no, this cannot work. But it doesn't rule out the possibility that you start from ETH and find an entirely different way that builds something entirely different in between and arrives at an Oneway function. It's still something that we hope to get someday.
Okay, so then just like a technical restriction, we will be considering oracle functions that only make queries to one particular length, and we haven't checked the proof of the general case yet to the point that I would like to claim it's true. We believe it's true, but we haven't checked that yet. Okay, so let me introduce the protagonists of this talk. So we have self-amplifying average case hard language, which average case will just look at the uniform distribution because this is what suffices for our purpose. You can come up with more general definitions. Self-amplifying essentially means that if instead of this is a decision problem. If you sample one instance, your success probability should be roughly a half. And if you sample L instances, then your success probability of getting all the bits of whether xi is in the language or not right should be something like 1 over 2 to the L. Of course, such an ideal result is a little bit too good to hope for. So you might want to take into consideration the complexity of this algorithm. So this algorithm A has some number of elements that it can decide trivially within its runtime. So when you think of instance size of n and witness size as n, in time 2 to the n divided by 2, you're very likely to find a witness for the language. So the cost of your function divided by a half times 2 to the n is the number of elements that you can decide trivially. And so, of course, those you don't need to guess. So for those, you don't get this type of loss anymore.
This is the definition of P?
This is the definition. This is the definition, but tailored, of course, to what I want to show to you. A theory of self-amplifying average case hard languages would probably look a little bit more general and different. And the second, so the second thing that I would like to do is it's if there is some constant, then this is still a very strong assumption. So and so this so how far does it amplify? Well, you should not have collisions. So if L, as long as L is not too big, this type of amplification works. Okay, so this is a self-amplifying average case hard language. That's the first protagonist. Second one is the one that later we will always say should not exist, is a fine-grained one-way function. And a fine-grained, so if you think about the definition of a one-way function f, it has the property that for all adversaries in some appropriate class, if you give the adversary, if you sample a random x, plug it into the function, give it to the adversary, then the adversary produces something, and the probability that what the adversary produces is the same as the input that the adversary got, this probability should be small. And so the definition of fine-grained is that that we just look for a polynomial gap between the adversary and the function that we compute, and as long as the adversary is only some like specific polynomial more expensive than the one-way function, the adversary should not be able to invert the function.
What is cost NF?
It's the time of the function. If you think in a non-oracle world, it's a runtime of the function circuit size.
Isn't it cost of F?
It's cost of f on inputs of length n. All results work for Turing machines and circuits. It doesn't really matter as long as your non-uniform input doesn't depend on the oracle. So we don't have pre-processing type things, but else it doesn't matter whether it's uniform or non-uniform. And so I left open the inversion property, and so usually here we have a negligible function, but what we're going to rule out are even fine-grained one-way functions where we only want 1 over n security. And again, we have some constant that we're happy to lose. Questions on the definitions?
So just to make sure if I understand, so self-amplifying, you're saying it's useful because we cannot, it's like Hardness amplification, right? So you want to say we won't assume ideal kind of Hardness amplification because we cannot prove it by reduction. That's why it's useful, okay.
Yes. So, okay. So
what's a language which is not self-amplifying?
I think most languages are not known to be self-amplifying.
Yeah, exactly. Do you have any example? Matrix vector multiplication. Sorry? Matrix vector multiplication. Once you have many vectors, you get matrix by matrix.
Let's say with its 1 and 3.
I'll take any random language where all words in the language have the same witness. Once you find a witness for one of the words, the program can tell you all of the languages.
Okay. So, so we want an oracle that separates these two, which means this self-amplifying average case hard language exists, and this fine-grained one-way function does not exist. Okay. So, so let's just do the negation of the quantifiers together. No fine-grained one-way function f means that for all functions f, there exists an adversary which whose cost is not too big, such that this adversary can invert with reasonable probability.
And again, what is epsilon? Is this epsilon or what? Epsilon there.
Yeah. Okay.
This is a gap, the hardness gap.
Yeah, that's the reason.
Yeah. And the oracle that we show will also depend on this epsilon. So we can show so for every epsilon we can show that there is no epsilon, that's an oracle such that there is no epsilon one-way function. Okay, so if you're in an oracle world, these probabilities are over oracles as well, and these algorithms, they are oracle algorithms, and these cost functions, we need to think about how expensive it is to make an oracle call. But for now, let's just say that an oracle call is just one step, and we'll see something else later. So for one-way functions, we usually go for a random function model. Now here we go for a random language model. So what is this natural hard random language? It's for each string you sample a witness and you sample a random bit. And you have a check oracle that if you hit the witness, it tells you whether it's in the language or not, and else the oracle returns what. So, and because the witness is valid for 0 and 1, this is a language in NP intersected Go NP. And this makes the analysis much easier because you don't have to distinguish between what you learn from check returning 0 and check returning 1. So the language is all x is such that bx is 1. We can use this NP formulation, and this is the complement of the language. By the design of this random language oracle, you need to make the witness queries for each x separately, and therefore this random language is self-amplifying. Okay. Okay, so far so good. So relative to this random language, we have a hard language, but unfortunately, we also have a fine-grained one-way function. No, we do have. So this oracle is a first attempt, but it's not good because it actually does give you a one-way function, which essentially says sample a bunch of values and a couple of indices of some security parameter which is much lower. Then solve the find the witnesses for the indices that you sampled and return the witnesses. And then an inverter needs to find the indices to which these witnesses belong. And to be able to do this in this oracle world, you need to solve most of these instances. Whereas the forward computation time is log n times you need to find a witness of time of length log n, which takes time n. So the forward computation is log n times n, and inversion is n squared. Okay, so that's bad. So we have an oracle relative to which we have a hard language, but also a fine-grained one-way function. Well, and this is this construction has some similarities with some construction that Andrea is going to show, which is very nice. Okay, so now what shall we do? We have an average case hard language. We have a fine-grained one-way function. So now let's add an oracle that kills the one-way function, and try to hope that it doesn't kill the language. So let's add an inversion oracle. You give it a y. It samples a random value from the set of pre-images of y and returns it. Okay, so far so good. Unfortunately,
F is an input to this oracle?
f is an input to this oracle.
And how is it represented? What does it mean?
It's represented as an oracle circuit. So far so good, but such a great inverter is a little bit too good. The reason is that this inverter that takes an oracle circuit f, so the cost of f tells you how much hitting queries or how much check queries that give you something else than what f should make, but if you take a function that on strange inputs has lots of hits, so for example, a function that on x and the witness just checks whether this is the right witness, and if it's the right witness, it outputs 1, and else it outputs 0. So here, if I put x1 to xl and d1 to dl, the pre-image is the set of witnesses, and this would allow me to invert this. This would allow me to invert this one-way function, but also to solve my average case hard language, to decide my average case hard language. Okay, so what we will do, therefore, is we will flatten our algorithm f, so that the inversion set that we look at actually considers a function that once it makes too many hits, it just replaces the oracle responses by bot, and thereby we eliminate getting free images that make too many hits and getting too much information from the inversion. So QF replaces answers to check by bot once the expected budget is exhausted. The question is, what is a good expected budget? Well, if f is very small and makes much less queries than 2 to the L.
What is L?
L is, f only makes check queries on one length, on length L, and this is the L. And if f makes far too little queries to have a chance of getting a hit, then we replace all queries to check gates by bot, because the function will still almost be exactly the same, and inversion will still work. And if it makes enough queries, then we define the budget such that you still should not make much more queries than you should not have much more hits than in expectation. But also there we curb, and so we need to enforce this budget on inverse queries as well. But I dropped this for now. So I already said that the flattening for the small f does not affect the inversion probability much, and for larger f, we have this 1 over delta in the exponent here, about which I will talk later. But just adding 2 hits is is sufficient because the number of hits is size of f. The expected number of hits is size of f divided by 2 to the L minus 1, and the probability of there being 2 more hits is at most 1/4, and this would suffice for our inversion probability of our one-way function. Okay, so inversion still works. So the question is whether L is still hard. And so why is L still hard? L is still hard because well, let's think about it. So the QF never makes more hitting queries than a circuit of the size was make with only check queries. The cost of a check query is 1, and now we define the cost of an inversion query appropriately, such that those two things align. So we give a couple of more hit queries here, but we also increase the cost such that the adversary pays for it, and thereby the inversion queries, they give you a couple of more hits, but they even out. So the second question is, what else do we learn? So we have check queries. We don't get too many check hit queries from inverse. The question is, what else do we learn from inverse? And this random sampling here is kind of really tough to deal with in proofs. So what we do instead, it's a very simple trick. We just give a pre-image if there is a single pre-image, and so to deal with this, we use universal hashing, which makes pre-images unique with some probability, and that's essentially going for a unique pre-image is the case, or is the reason that we get this 1/n factor here, and this flattening is the reason that we get a constant here. Okay, so now I think I have minus 2 minutes to talk about the hardness of inverting L. So let me try to say the main points. Okay, so here we have our inversion oracle, and we have our check oracle, and we know there's no fine-grained one-way function relative to these oracles. But what about the hardness of L? So we said inverse does not give us more hitting check queries than an algorithm using only check of roughly the same cost. And in addition to hits and non-hits, each inverse query gives us at most one free bit of information, namely the bit of information that says, is there a unique pre-image or not? It's a single bit of information. And that's very little, which is super nice. So thus, as long as you only query inverse with F, you get as most twice as many membership bits as you would when using the same query strategy with only check. And so this is absorbed in the constant in our cost function earlier. And so the second question is, how do free bits increase the hits of these check queries? And there we have a very nice core lemma that essentially designs a trivial strategy that I will not go into now, and proves that any adversary cannot do better than the trivial strategy. And for the free bits, essentially each free bit only halves the number of witnesses that the adversary needs to go through. And these are the main proof ideas to show that this function is self-amplifying average case hard. Okay, so let me summarize. This is our oracle, and relative to the above oracle, self-amplifying average card. There is one self-amplifying average case hard language in NP intersected co-NP, while there is no fine-grained one-way function. So open question, how to circumvent this result. So you can circumvent this result with assumptions that our oracle does not satisfy, and then prove those assumptions from worst case assumptions. Maybe you could also circumvent our result with non-black box techniques. We have no idea. We've thought about non-black box techniques that would help. So I would be very happy to hear about anything that comes to your mind. Thank you.